So once again, I'm going to be talking about a project that's nearing conclusion, and this is on establishing bridge column capacity limit states, primarily through modeling and simulation. I want to acknowledge my co-author, PhD student Jin Zhou, who's also on the line here, um, and will take over from me in case something, goes wrong during this presentation here. So, what happened here? Okay, there you go. So in terms of the outline, I'm going to first give you a little bit of background. This has to do with ShakeCast, a software platform used by Caltrans. And then I'll talk, more about the development of these component, or rather in this case, column capacity limit states, the conceptual basis for the modeling, and then talk about two types of approaches that we followed. We started with a ductility-based approach to these limit states, and then moved on to damage-based, and try to explain the reasons for that. And then how we applied them to multi-column bends so as to actually use them in post-earthquake assessment. Okay, so we'll conclude with some primary findings and some additional work that's still ongoing. So talking about ShakeCast, okay, so ShakeCast, like I said, is a platform used by Caltrans, and this is for near real-time damage assessment. So the moment there's an earthquake, USGS generates the ground shaking data, and what ShakeCast does is it looks at its inventory of existing bridges in the vicinity of the earthquake, and then looks at existing demand models in the database to assess possible damage to the bridges around like I said, in the vicinity of the earthquake. So the idea here is to associate the demand experienced by these bridges with likely damage. All right, so of course you need both component level as well as system level damage states. And like I said, this study is focusing primarily just on the column itself and not on the system. And so just to mention, a lot of this work, actually Caltrans has funded a pretty large project at Georgia Tech along with Rice University, and they have gone through and created a pretty large experimental database. They're talking about experimental data. Now this data is actually available on DesignSafe, and I can share that information with UCLA later on as well. So this again is these are primarily columns tested in the US, Japan, and New Zealand. However, when we look at the database that they have compiled, it's fairly limited, especially when it comes to older bridges. Okay, and I'm talking about pre-1971. And so that's the reason we said, okay, why don't we try to do some numerical simulations to add to the available experimental database. So, like I said, there already exists now in DesignSafe the data that has been compiled by the Georgia Tech group, in conjunction with Caltrans, and they have classified the bridges into 3 eras. As you can see here, there's an era 1, 2, and 3. And I am going, and the focus of this particular project is to just look primarily at era 1, because this is where we expect most of the damage to bridges. Some of the more modern bridges are pretty well designed, and we don't expect, extreme damage to some of these modern Caltrans bridges. So since this is all about modeling and simulation, I thought I'd spend the first few slides talking about the kind of modeling that we used for all of our bridge columns. So as you can see, essentially it's a force-based beam column element with 4 integration points. We also have a shear spring to model potential shear failure. We also have bond slip and a zero length section to model possibly shear penetration effects. And so what we did here initially was to compare different modeling choices. So I'm just showing you one plot here, but we had 3 different options here where we subdivided the column into multiple elements. We had a single column element, and then we finally compared that with a non-local formulation. That's something that a former PhD student of mine worked on, And so based on that, we chose a particular beam column element with a suitable number of integration points that came closest to the non-local model. And here again, very quickly, in terms of confinement effects, we looked at both circular and rectangular sections. And so we used the Mander model for the circular, and we used a different model proposed by Sashi and Razvi for the rectangular sections. In terms of shear penetration, many of you may be familiar with the work of Sridharan and his group at Iowa, and so we use his model. And again, another former student of mine had done a lot of work on rebar buckling, and so we used that model to simulate bar buckling in the longitudinal steel. So in terms of, since we're using a fiber section-based model, we were essentially monitoring the material response in concrete and in steel. So for example, in concrete, we would look at things like, when does cracking start? When do you have the onset of crushing in the core? In terms of reinforcing steel, we use the hysteretic material. And here again, we talk about the initiation of buckling, bar rupture, and so different states that we can monitor during the simulation, and then eventually to correlate them, with other parameters. So we first validated these models with experiments, and so here I'm showing you three cases here. All of them are non-ductile columns, and here are the references to these columns tested by one of my colleagues here, Chai, in 1991. Here's another one tested in New Zealand, and this one in San Diego. And as you can see, these were primarily flexure, but here in these two columns, we also see some shear degradation, after certain ductility. So we used, the model proposed by Sezin and Elwood and the group to model, shear deterioration as a function of ductility. Okay, I'm not going to get into too much details on the modeling side here, so as to be able to get into some of the results. So how did we, come up with the columns to simulate? We looked at the Caltrans inventory of columns, and so here what I'm showing, each one of these dots represent an actual column in the Caltrans bridge inventory. So this is the H/D ratio, and as you can see, the majority of the bridges, some of them have lower H/D ratios, but most of them, I would say, have an H/D of 4 or higher. And here again, for different diameter columns, I'm plotting here the transverse versus longitudinal reinforcement ratio, trying to see if we can come up with a subset of columns that we can use in our simulations. So we eventually generated 7 columns, and as you can see the transverse and longitudinal reinforcement ratios that we picked to fall within the broad classification that I showed you in the previous slide. So in addition to that, we also varied the hysteretic parameters in our reinforcing steel model to generate additional simulations, because we wanted to get some variability in our response, so we could plot some fragilities and get median values. And we also used 3 different loading protocols. We used 1 cycle at each displacement amplitude. We used 2 cycles, and we used 3 cycles just to see the effect of loading protocols. So, in all, each of those columns are essentially subjected to 9 simulations, 3 3 variables with respect to the modeling parameters, and 3 with respect to the loading protocol. And eventually, we also subjected them to seismic motions. I'll talk about that in a minute. And so, like I said, we looked at both circular and rectangular columns. And here we're talking about, which sections in the core, in the cover, and the steel that we monitored, both for the circular sections here on the left and for the rectangular. And again, I want to mention here the rectangular sections we looked at are these wide, what we call wide rectangular sections. Okay, there are quite a few of these types of sections in the older California bridges. So in phase 1, what we did was to basically calibrate these strain limit states, as I would call them, with ductility. Okay, so here I'm just showing you a couple of samples. I actually made a longer presentation on this at the previous workshop. So this time I'm going to focus more on a different approach that we took. But the bottom line is in a fiber section model, as you can see here, you can monitor the strain in the concrete, in the steel, and thereby classify these limit states. So in phase one, essentially, we were just looking at the ductility of the column. All right. However, when we started to apply them in earthquakes, we ran into a problem. Okay, the problem being that, the maximum duct in this particular example, I'm showing you the force displacement response of a particular column under an earthquake load. And as you can see here, the maximum ductility is obtained, was achieved here a bit around damage state 5. All right. But however, with additional loading, you have damage state 6 and 7 because of things like low cycle fatigue and crushing of the core and so on happening at lower ductilities in future cycles. So by using a ductility-based model, we were just not able to capture these what I would call extreme damage states. And I show you some of these results here. If you were just focusing on cyclic loading, then because you keep on monotonically increasing these cycles, as you can see here, this is the mean of all the cyclic loading. You can see a nice trend here that you can pick up damage state 5, 6, and 7 at increasing displacements. Whereas when it comes to seismic loading, you're essentially, you're just capturing the same 4.15 for all the previous limit states. So basically the conclusion was that, using ductility by itself will probably be not adequate if you're going to start to look at damage to these older California bridges. Okay, so we then moved to a damage-based approach to coming up with these limit states. So now we're talking about concrete damage. Okay, so essentially we're monitoring the stress strain response in the core, primarily in the core. And we came up with a model for how damage will progress before it reaches the crushing and after. So, so initially the damage progression will be at a certain rate, which will then increase once you hit the peak, and then you see the softening portion. So you have, a concrete damage index. Likewise for steel, we primarily use a fatigue-based model where this N sub F, 2N sub F is the number of half cycles to failure. And then once you had the damage to the concrete and steel fibers, we would aggregate them using weighting factors. Okay, and so again, the weighting factors are a function of the damage indices themselves, but in addition to them, we also included some parameters here as shown by alpha and beta that indicate the location of the fiber. So the further, within the core that this damage happens, these factors, would have higher weighting factors. And ultimately, to get the damage in the column, again, we just used the damage in the steel and concrete at the cross-section level to come up with the overall column damage index. Okay, so important things is we had to, also monitor things like buckling, which is not an easy thing to do, especially for cyclic loading, because in the monotonic situation, if let's say we defined a strain at buckling, if you experience tension cycles here, you've got to shift that origin, from 1 to 2 to 3 as the bar also experiences, say yielding and tension, which happens as shown here in an actual simulation, that a bar first undergoes yielding and tension, and then so when we talk about buckling, strain is not further out here, but with respect to this plastic strain in the tensile side. So with information like this, we were able to come up with 6 or 7 different damage states, all the way from cracking in the cover, all the way to collapse. And so again, you can see here the first few damage states are primarily controlled by the concrete. And then when we get into the extreme limit states, it's mostly in the reinforcing steel, starting with bar buckling, an exposed core, or the rupture of the first bar, depending on which happens first. And so we have all of these criteria that helps us distinguish these different damage states.
About 2 minutes more.
All right, thanks. And so we looked at, so after we came up with these definitions, we actually applied them to a couple of the columns, that we have validated our model against. And as you can see, we get fairly consistent results in terms of the damage index corresponding to a damage limit state. Of course, the more difficult one to calibrate is collapse, because things like collapse are actually not very well defined in most experiments. We also calibrated this with a shaking table test that was carried out at UC San Diego. And again, so these were 3 sets of ground motions, and as you can see, these were the initial ground motions that were applied, and these GM2 and 3 reflect additional ground motions, after many cycles. And so we were able to kind of reasonably capture the progression of damage all the way to a multi-bar rupture in that particular column. All right, so in terms of, after we generated this data, what we did then was to generate a whole bunch of bridge bends, single column, 2-column, and 3-column bends, such that they all had similar lateral capacities, and then ran them through a bunch of ground motions. And so here we selected the FEMA P695 ground motions. There were pulse-like motions and non-pulse-like motions, and so we subjected our single 2-column and 3-column bends to these ground motions, did a whole bunch of IDA simulations, and here I'm just showing you a sample for the single and 3-column bends, and then to plot these fragilities as a function of an intensity measure here, we used SAT1, which for bridge columns tends to be a fairly reasonable metric. And here I'm showing you, damage stage 6 here. In this case, I'm just looking at pulse-like and non-pulse-like motions for a single column bend and for a 3-column bend. And so the bottom line is that with the damage definition that we have, we can plot fragilities like this. Okay, and this I think is the final plot I'm going to share with you, comparing the response of single, 2, and 3-column bends. And what's interesting to note is that in an early damage state, this is damage state 2, you will see that in fact a 3-column bend will perform better than a 2-column, which will perform better than a single column bend because of things like redundancy. However, interestingly, at higher damage states, we find that a 2-column and a 3-column bend will essentially perform very similar, indicating that redundancy effects essentially are, beyond a 2-column bend. We don't seem to gain any additional benefits. So in my concluding slide, I just, the few comments I want to make is that a ductility-based limit state is probably not going to be as reliable for earthquake loading, and the damage-based state that we have proposed, was shown to be independent both of the failure mode and the loading protocol. And now I did not present results here of other failure modes, but we do have, simulations of mixed failure as well. And then, as I just showed you in this previous slide, that the redundancy provided by multi-column bends indicate that 2-column bends do provide additional margin of safety, but no further enhancement is achieved in going from a 2-column to a 3-column bend. So, we're still working on a few other things. We are trying to refine the damage model for early limit states. We still have some issues with that. We also want to look at additional cross sections and spend a little bit more time on multi-column bends looking at mixed failure modes. Okay, earlier today I saw some work presented by Farzin at UCI on damage indices, and I certainly would like to, collaborate with him to see how we can extend our work to compare some of our findings with some other work that he's doing. And that is all. I just want to acknowledge, by the way, at the end, Cliff Robley at Caltrans and the group at Georgia Tech, who I've also been collaborating with on this work. And with that, thank you very much.
Right. Thank you, Sashi. And do we have any questions for Sashi that you'd like to ask right now? Okay, so let's see, Farzin, I see your hand up. Do you want to ask?
I was trying to figure out how I'm going to unmute myself. I didn't realize that you need to unmute me. But Sashi, beautiful presentation. Thank you very much. While you were giving the presentation, I was thinking the same way. It would be great if you and I can sit together, because the work that we are doing, there is zillions of a lot of simulations going to happen, and we can make a comparison between the detail of our models. Was the second part of my response to your question early in the morning. And then how would that impact the work that the engineers will do? Because they like to work with damage in this index. But from your presentation, I realized that there are other EDPs that can, let's say, that you're gonna get the damage states with lower variability.
Yes, yeah.
So let's definitely discuss in the next couple of days.
Yeah, absolutely, absolutely. And that's why I actually added that little statement just after I listened to your talk, that we need to talk about this, and probably also need to talk a little bit with Khalid and Salim on their project, with the Brace project, where they're also looking at limit states.
Absolutely. Thank you so much.
Yeah, sure.
I see there is Salim, you have a question as well.
No, I mean, I actually, this was a great presentation. Like also, as Professor Kunnath mentioned, there's great overlap. So yeah, that would be great too. Yeah, I learned a lot from just these set of slides, but we can talk with them further. Thank you.
Yeah, welcome.
So I do see, Sashi, that there is one more question from Kathy, which says that the chart shows that there is no column collapse. And so was the gravity load applied vertically, or was this the expected failure mode? So Kathy, if you, I don't know, I think I paraphrased your question correctly, but if you are somewhere online, if you wanted to pipe up and ask that question.
So again, so you say collapse was not shown here. So yeah, so collapse is an extremely difficult state to capture, and the way we defined it here was a 50% loss in the lateral strength. Okay, and in some cases we just didn't achieve that. We simply had so many bars rupture that at the end we decided that damage stage 6 was sometimes the same as damage stage 7. For example, in the full-scale test done at San Diego, the column really didn't collapse. And okay, so in our case, the vertical load we're applying is the axial load in the test. And bridge columns typically don't have very much axial load. They're about 10 to 15% maximum. And so to actually get a gravity collapse, is kind of difficult. So I would say that, damage stage 6 and 7 kind of merge to some extent. When multiple bars rupture, we basically call that collapse as well. I don't know if that, adequately answers the question.
Yes, thank you, Sashi. You answered my question.
Okay.